Hey folks, I'm Domotro, here in my room because it's raining outdoors on my combo classroom right now, and we're basically at the end of grade -1 here, which is why I've cut the rest of my hair a bit more, and why I'm in between lab coats, all of which will be explained more in the official ending to this grade, a documentary-like finale episode that will be coming out on the main combo class channel this Friday. But another part of wrapping up this grade was a little final exam that I made a video and text version of that gave my viewers an opportunity to test their brains on some mathematical problem solving, among other things. And in this video here, I want to go through the rest of the answers and the steps you could use to come to those answers of the remaining questions of the mathematical part of that final exam. I've already made 2 videos in this little trio of answer videos, which went over questions 1 through 11. So now in this video, we'll go through questions 12 through 21. And whether you're the type of viewer who did the test already, or on the complete opposite end where you didn't do the test and don't expect you will in the future, you should watch through how I come to these conclusions of these answers, because it might give you some cool problem solving tips or tricks and mathematical tools in general. Although if you're in the middle of that scale and you haven't done the test but think you might at some point in the future, maybe click on the test video instead, which is linked in the description here, and see if you want to challenge your brain on these questions. In any case, here I'm going to go through one at a time, each of these answers, as well as a brief couple steps of how you could solve them. In this first question here, number 12, I asked, if a number has 5 prime factors, 2 of which are the same as each other, and the other 3 of which are distinct, or otherwise known as different, not allowed to be copies of each other, how many total positive factors does that number have? So prime factors are when we break down a number's factors into the smallest possible integer units. And these prime factors of a number can be written in something called the prime signature, which just tallies the exponents on each of the prime signatures in the factorization, or in other words, the multiplicity of them, how many of them occur a single time versus a certain amount of multiple times. So we could write the prime signature of this number that they're telling us about in the question, or that I'm telling you and myself about, as 2, 1, 1, 1, which is the prime signature way of saying there is a prime that has 2 copies of it. It would be written as it squared in the factorization, and then there are 3 separate primes multiplied together. Now, in my episode on the main combo class channel about prime signatures, I showed how these do give us enough info always to know how many total positive factors there are. There's a simple, cool formula, which is that you take each of the numbers in the prime signature and you add 1 to each of them, so the 2 became a 3 here, and each of the 1s become 2s, and then you multiply them together, which gives us 3 times 2 times 2 times 2 is 24, and that tells us 24 positive factors, or as you'll often just hear them called, factors if you're not specifying the negative ones, of this number. And there are many numbers that fit this definition, but funny enough, this prime signature is asked about again a little later here on question 16. So I will actually jump to that one right now, question 16, because we have a similar thing going on here, but now instead of being asked, how many total positive factors does that number have? I'm being asked, what's the smallest number that represents that? This won't necessarily be the smallest number with 24 positive factors, but it'll be the smallest number that has this prime signature, and it will have 24 positive factors. out of these 5 prime factors, because other prime signatures may add up to 5 prime factors and result in a different amount when we do this equation, but all of the 2, 1, 1, 1 numbers will have 24. So what's the smallest? Well, the way that we could calculate this is by noting that the way of minimizing the size of this number would be to have the doubled prime, the one that has squared in the prime factorization, or 2 copies of it multiplied together, be the smallest possible prime. We're going to want it to contain 2 to the second power, because we need something to the second power in our prime factorization, and having that be a 2 will minimize the size compared to if a 3 or 5 or 7 gets squared. Next, we'll have 1 of each of the next smallest possible primes. They must all be distinct, so I can't make them all 3. I have to make 1 3, 1 5, and 1 7, which gives me that the smallest number with this prime signature would have a full prime factorization of 2 squared times 3 times 5 times 7. And that gives me the number 420. Presumably the reason this number is talked about so much in culture. If you ever see this number discussed as part of a meme or other cultural phenomena, it must presumably be due to it being the smallest number with this prime signature. It's also, fun fact, the smallest number that is divisible by anything between 1 and 7. By any of the whole numbers between 1 and 7, this can be divided by with no remainder, and no smaller number has that trait. So, next, we're going to move to 13, which asks us, what is a number where if you add 5 halves to it, you get the same thing as if you multiply it by 5 halves? Now, there was an episode where I went over the formula that you'll always get when you want to add 2 numbers and have it be the same result as when you multiply the same 2 numbers. But let's say you don't know that formula and you want to solve this case by scratch. You could do this particular one with a little bit of simple arithmetic. We can note that our number n here plus 5 halves equals n times 5 halves, which is 5n over 2. Now, if I subtract n from each side here, that subtracts the n from that side, and it subtracts 2n over 2 from this side, leaving 5 halves amount of n's as 3 halves amount of n's, because 5 halves is 1 greater than 3 halves. Now if I multiply each side of this equation by 2, I can see 3n equals 5. And if I divide by 3, I can see that n equals 5 thirds, because we had 3n equals 5. So n equals 5 thirds. And it's true that if you add 5 halves plus 5 thirds, you get the same result as if you multiply 5 halves times 5 thirds. And so that is our result of our number n. Next, for 14 here, I asked a question about what's called tetration, the level beyond exponentiation. I asked, what is 3 tetrated 2 minus 2 tetrated 3? Now, tetration refers to a stack of exponents with the amount in the stack, including the bottom one, being the number we're tetrating 2 at the end, and the number that's in the stack all being the first number here. Similar to how exponentiation can be seen in pretty much all normal cases as repeated multiplication, apart from extensions we need to give to exponentiation when we work on the complex plane and so on. When we're working with simple general cases like 3 cubed, we can see that as a repeated multiplication. tetration can be seen as a repeated exponentiation in most cases here. And we're going to see that as meaning 3 tetrated 2 must mean a stack of 3 to the 3's that is 2 of them total, meaning just 3 to the 3. That is a stack of 3 to the 3's with 2 in it, including the one at the bottom. And we said, what's that minus 2 tetrated 3? Now, 2 tetrated 3 is going to be 2 to the power of 2 to the power of 2, which we're going to have to write, if I'm not writing it in the stack, which this text document doesn't allow for format-wise, as that. I'll put parentheses to be sure people know, because when we see it as a stack of exponents, the convention is to read it from top downward. And in this case, it actually would not matter, because 2 to the power of 4 is the same result as 4 to the power of 2. But it's somewhat coincidental that in this case, it didn't matter, because in almost all cases of tetration, it will read and become a different thing if you interpret it from the bottom upwards as the top downwards, and the top downwards has been picked as the convention. Although in this case, either would result in the same because of how 2's work when you have this amount of them. In any case, we know what these are. These are easier to break down in our head. 3 cubed is 27. 2 to the power of 4, which is here, is 16. We have 27 minus 16. That gives us 11. So our answer there is 11 by us getting 27 minus 16, essentially. Next, I asked, what is the only multi-set, meaning a set or collection of positive integers in this case, but multi-set is a clarifying term to mean we can allow duplicates of them. They don't all have to be distinct. Of 24 positive integers, where if you add them all up, you get the same result as if you multiply them all. Once again, something that I went over in an episode on the main combo class channel, and you would have had to see that episode or have read about this particular topic to know that it's the only multi-set, that there's only one case of 24 positive integers that can do this. But whether or not you knew that, you might be able to deduce this answer. The answer ends up being 22. Let's get the right amount. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Ones, a 2, and a 24. And if we add each of these together, our result will be 24 plus 2 plus 22 by having 22 ones, which gives me 48. And if I multiply these all together, I also get 48. And so this is a multi-set of 24 positive integers that does that. As it turns out in the episode I made about these, this is the only multi-set of 24 positive integers, but it's an open question as to whether there's an infinite amount of numbers that only have one multi-set possible, such as 24 here, and this being the only possible one, it turns out. In fact, the largest known number that there's only one multi-set of that many positive integers that can do this is 444. It's an open question if there are any beyond that. Which brings us to question 21 in a way. What are 5 open questions or unproven conjectures in math? I'll mention that one for now, that is an open question. Now, number 17 here asked, what are all the possible values that a prime number larger than 3 could be congruent to in mod 18? Now, this is similar to another question when I asked about last digits of bases, but I was asking about square numbers then, and now I'm asking, that was on an earlier part in an earlier question than 12, but here it's a little different anyways because we're asking about prime numbers, whereas that one was about squares. Now, as I showed in an episode about spiky shapes, we can know the possible values that prime numbers can be congruent to in a mod if the prime number is larger than the mod number, although in this case I did just say larger than 3. We'll see that that still works. by finding the values of number that are smaller than the mod number and what is called coprime to it, or that are relatively prime is another term, meaning no factors in common greater than 1. For example, the number 12 isn't a factor of 18. You can't divide 18 by 12 without needing a remainder, but 12 has factors in common with 18, 2s and 3s and such, even a 6 in common. And so 12 is not coprime to 18. They share a factor. And you can go through some logic by looking at a number line or other ways to deduce that, well, I couldn't have a prime number that's 12 more than a multiple of 18, because if 18 is even and threeven, so would that one. It would be even and threeven also. And you can go through similar logic to see if I was a prime larger than 18, I would need to be congruent to a value that's coprime to 18 and smaller than it. The values of which that don't share any factor in common with 18 and are smaller than it, being 1, 5, 7, 11, 13, and 17. Basically, the primes larger than 3 but smaller than 19, and the unit 1. And these are the values, because even if I said, well, I only asked larger than 3, and this is mod 18, well, we did cover all the primes in between there. So all of the primes themselves, the primes 5, 7, 11, 13, and 17, are covered by this because they're congruent to that. If they're it itself, they are that much more than the 0th multiple of 18, 18 times 0. And so here, we actually have this covered as our full set of values that a prime number larger than 3 could be congruent to, because it covered all the primes between 3 and the mod number, and it covered, by adding that 1, all of the future primes bigger than 18 by them needing to land at a spot that was coprime using this modular arithmetic. For more details about that, see my episode about spiky shapes. Now, next we asked on the complex plane, how many of the 8th roots of unity are on the real number line? Now, the 8th roots of unity are the roots of the number 1, the 8th roots here. So it's asking what numbers can you raise to the 8th power and get 1? And essentially, the easiest visualization was on a clock I made. And I'm not sure where that clock is at the moment, but if you imagine a circle on what's called the complex plane, where we have real numbers here, imaginary numbers here, and combos of them in other parts, and we imagine the unit circle that has radius of 1 and centered at the origin, we are going to equally space out 8 dots on it, including one at the spot for the number 1. And if we imagine 8 evenly spaced dots, 2 of them are on what's called the real number line and have no imaginary component. The numbers that that's true for are the numbers 1 and the numbers -1. And so there are 2 out of the 8th roots of unity on the real number line. Now, if we had asked about the 7th roots of unity, if you imagine putting a dot where the point 1 lives on the complex plane, which is basically, if you were on an XY axis, 1 in the direction of what you'd normally call X being positive, then scattered 7 equally spaced dots, including it on a circle, you wouldn't get 1 on the point -1. The other 6 points evenly spaced wouldn't hit exactly opposite on -1 there. You need an even-th root of unity to have 2. So the answer will be 2 for any even number here, like 6th roots, 10th roots, 12th roots, and the answer will be 1 for any odd number, because it would include the number 1 as an 8th root, but not the number -1. You can also imagine that algebraically that the number -1 only raised to an even power becomes positive and becomes the number 1, raised to any odd power, it bounces back to being -1. Next, I asked, for each of these numbers, list at least one of its positive factors apart from 1 or itself. Now, each of these numbers has multiple factors you could have listed, so this isn't going to be the only right answer, but this is going to be the answers that I had in mind for a factor that we can locate within this number just by knowing a pattern about numbers. Now, all of these, if you look at them, are palindromic. They read the same in both directions. We have climbing up through 5 and back down, and we have a more scattered palindrome with an even amount of digits. And here we have climbing up through 5, then a 0 in the mix, and then 5 going back down. Now, this first one, that is a staircase from 1, 2, 3, 4, 5, 4, 3, 2, 1, I've mentioned happens to be equal to the amount of ones in a hyper-11 or rep unit number, the height of the staircase, squared. So we have that number squared gives us this. And although that is not the full prime factorization, this could be broken into smaller primes. That is a factor of it. So we can say that this number, 11,111, is a factor of this, in fact, in almost a double way, because we can square this to get that, although we would only include it once on the list of factors. Now, next we have a palindromic number, but with an even number of digits. Now, I've mentioned in my episode about palindromic numbers that if they ever have an even amount of digits, we know that they are a multiple of 11. And that's because of a divisibility trick that works for the number 11, where if we take the digit places that are sort of interlocked, the ones in odd positions and the ones in even positions, we add up each of those and find the difference. So the difference between 1 plus 2 plus 5 plus 2 plus 0, and the same thing backwards, which in this case, the difference would be 0. If that difference is ever a multiple of 11, including 0, which is a multiple of 11, then the number itself is divisible by 11. And so we know that this must contain 11 as a factor. Here we have one that doesn't follow either of those palindromic rules. It is not one where if we play the 11 game, they perfectly interlock because it doesn't have an even number of digits. And it's not one that has this type of hyper 11 squared form due to that 0 in it. However, it follows an even simpler rule that I've mentioned, which is if we add up the digits here, 5 plus 4 plus 3 plus 2 plus 1 twice, that adds up to 30. A three-even number. And if the digits of a number add up to a three-even number, so does the number itself. So this must have 3 as a factor. And of course, there are other possible answers. So if you answered something other than these and you want to check it, you can just look it up. And if it is a factor apart from 1 or itself, it is another correct answer. Next, we have ones with many correct answers. So I'm not even going to write any down here. I'm just going to name a few examples. Here I asked to list an example of each of these following types of number. First was a highly composite number that isn't a factorial. Now, there's an infinite amount of answers here, and that's because there's an infinite amount of highly composite numbers, and only the first 7 factorials are highly composite. And so we can't answer some of the classic highly composites due to them being factorial. We can't answer 1, 2, 6, 24, 120, 720, or 5040. Those are the highly composite factorials. But we could answer any other highly composite number that I've discussed the high divisibility of. For example, it turns out 4 is technically highly composite, although it doesn't get discussed in terms of divisibility quite as often, but it does have more factors than any smaller whole number, and that makes it highly composite. And one that I had in mind that some people might answer was the number 12. 1 dozen. A dozen is so divisible that we use it in all sorts of measurements throughout society, and it is highly composite. It has more factors than any of the smaller previous integers. And it's not a factorial. Next, I asked a deficient number which isn't prime. Now, technically, the number 1 is considered deficient, and it's not considered prime, so you could answer 1. But deficient means that its factors apart from itself, its proper divisors, add up to less than itself. And all prime numbers are deficient, but there are deficient numbers that aren't prime as well. And the next answer that could be 1 is also the number 4. Can answer this one as well. The number 4 has its positive factors apart from itself add up to only 3 because they're 1 and 2. And that's smaller than itself. And it's not prime, so we could answer 4 there. Next, we got a semi-prime number that isn't square. And a semi-prime, sometimes known as a biprime, is a number that is made of 2 primes multiplied together. And some of them are square because the number 4, for example, is considered semi-prime by having 2 primes in its factorization, even though they're both 2's. 2 squared can be called 2 times 2, and there are 2 primes, but not 2 distinct ones. And so we're asking for a semi-prime number that isn't square, which essentially will be the type of number that has a prime signature of 1, 1. Kind of like we talked about those earlier prime signatures. It will have 2 different primes multiplied together. For example, the number 6. 6 is composed of 2 times 3. It is a semi-prime that isn't square. We also could have answered something like 15, which is 3 times 5, or 21, which is 3 times 7, or anything else which is 2 distinct primes multiplied together as its factorization. Now, lastly, for this one, we had an algebraic number that isn't rational. Now, algebraic numbers include our good old rational numbers, as well as some of the irrational numbers. Irrational numbers are numbers that have, when you write their decimal in a base, it has an infinite non-repeating form. And irrational numbers cannot be written as a fraction of integers. And here we cannot answer something like pi, because while that isn't rational, it's also not algebraic, it turns out. It's a family called transcendental. However, any square root of a non-square integer would count as an answer here. The golden ratio would count as an answer here. Square root of 2 is a classic one you could have put here, or the golden ratio, or square root of 3, or cube root of 3, or plenty of numbers like that, which are considered algebraic but not rational. And lastly, for the mathematical section, I asked, what are at least 5 open questions or unproven conjectures in math? And there are tons of answers you could give to this. There are many classic open questions discussed, such as the Collatz conjecture, the Riemann hypothesis, the Goldbach conjecture. And those ones that I just mentioned were not explicitly described or didn't have full episodes about on the Combo Class channel yet. And so I'll mention here a few that I did mention explicitly on the Combo Class channel at some point, which include the twin prime conjecture, whether or not there's an infinite amount of prime numbers that are 2 apart from each other. Questions about what are known as perfect numbers, such as whether there's an infinite amount of perfect numbers, and another open question being whether there are any odd perfect numbers. Similarly, with multi-perfect numbers, we don't know if there's exactly 6 3 multi-perfect, or known as tri-perfect numbers, or if we might find more than 6. And there are questions similar to those perfect numbers about other things related to aliquot sums and aliquot chains when you add up a number's proper divisors, such as we don't know exactly what types of clubs or cycles form between numbers when you iterate the process of adding up their proper divisors. There are many open questions within that. One that I mentioned a minute ago is we don't know all the details about which sets of positive integer can be added to have the same result as multiplied. There are some numbers with the largest known being 444 that only have a single solution, which is of a similar form to this. But we're not sure as mathematicians yet if there are any beyond 444 with that property, that this solution, one of this form, or a similar one, if you see my episode about that, will, if there's any beyond 444 where this is the only possibility, something similar looking to this with a series of ones, then a two, and then the size. There are also other open questions about prime numbers, for example, we've discussed on the channel. It's not known whether there's an infinite amount of certain types of primes, such as the ones called Wilson primes. It's also not known if there's any of a type nicknamed double Wilson primes, if any of those exist even. And other questions about prime numbers. I'm not sure if I mentioned these ones explicitly on the main channel, but whether there's an infinite amount of primes that are right next to a factorial number, some things like that are open questions. And there are many other ones I've mentioned on the main channel because I find open questions and unproven conjectures quite interesting, especially these ones in the field of what you could call number theory, where they could be written in an algebraic way often as some question posed as an equation, wondering if this equation holds or doesn't, but they also can often be described in fun, casual terms. And so those are the answers to the math section, although these last two had many possible right answers, and this one had a few possible right answers here. And the next sections on the test were an opinion-based section, which I feel like I already sort of did in a lot of the combo class episodes, my opinions about certain societal structures. And there was an appreciation section, which you'll definitely get to see more appreciation within the finale episode I mentioned, the documentary-like long episode coming out on the main combo class channel this Friday that will be about creating grade -1 and now transitioning to grade -2, and includes a lot of appreciation as we look at the nature and the elements and such. And I will also be live on this channel at 6 p.m. for an hour or two, 6 p.m. Pacific time, tomorrow, Thursday this week. And I'll let you know then what my live stream schedule for next month might be like. But right now we are wrapping up grade -1. I'm very excited for grade -2, and there are some tricks up my sleeve I haven't shown you yet. So I will catch you again in that live stream tomorrow and in that documentary episode on Friday. Make sure you are also on the main combo class channel ready for that. Thank you all for watching this. Love you all so much, and I'll see you again soon.